So welcome to my talk, the GNU Radio Architecture Update. So this is actually a three-part talk. The first part of which I will hold, which will be more a bit of a review of what happened since last GRCon and a bit of an outlook of what will happen to the smaller scale of things. And then there will be two talks by Basti Blössel and by Josh Mormon about the future of GNU Radio. So with that being said, let's dive right in. So what's the current state of GNU Radio? If you remember, GNU Radio 3.7 was released 2013, and then a long time, nothing publicly visible as minor release happened until 3.8 happened right before GRCon last year. So in that time, we had a next branch where a lot of the future aiming development had to happen, but that next branch had no very close relation to what was released as software, which put a lot of developers under a real problem, namely that they didn't know when a feature that they wanted to add would end up in something that actually was called a GNU Radio release. So that was not optimal in terms of development velocity and motivation for a lot of developers. So when we released GNU Radio 3.8, we changed that model. We had only two branches now, one for each release series. So that was main 3.8, where all bug fixes went, so that 3.8 would be a maintainable release series, and we had the master branch since then, where all the features should go, and which should at one point become GNU Radio 3.9. So with that in mind, let's look at these branches in detail. So we've got 3.7, which is our still maintained legacy release series, which of course still gets bug fixes. But we're very conservative about breaking it. Why? Because it's our legacy code. Like there's 6 years of development depending on 3.7, and we have no intention of hurting these people. But on the other hand, we can't really add new features to that because the state of the code really just doesn't allow us to efficiently extend that without breaking anything. So that is our legacy release, and we have the 3.8 stable release series, right? Which is whatever you're doing with GNU Radio, if in doubt, you probably want to install a GNU Radio from the 3.8 series. These releases get all the bug fixes. We're making sure that 3.8 is available on next year's current machine. It's still available on next year's current favorite Linux distro. If these features are easily portable from master to 3.8 without breaking anything, well, there's going to be new features. And the good thing is it's basically packaged for all major Linux distros, so it's really easy to install. And as said, 3.9 is what, or will be what master is now, so all the new features will end up being in a release pretty soon. So what will that release at least entail? Well, I can tell you what the state of the master branch and thus what will be 3.9 is of today. So since we've released 3.8, 659 commits have happened. And since that was 30 months ago, that means an average of 1.65 commits a day, roughly. So that doesn't sound very much until you realize that this is mostly a C++ and signal processing project, and a lot of these commits are really, really, really large change sets. So this is highly involved technical work, and I'm pretty happy about this speed. So we're way past our expectation there. We can also count the lines that have changed, and this is a ridiculously large number. That may have only two reasons, which I go into shortly. So let's not focus on that. What I really want to stress is that we have 88 contributors for between 3.8 and what is the current state of master, and of which 50 are new. So they have no commits in 3 that I could find without cross-checking email addresses. So this is a rather healthy community because it means that although this is a highly technical project, we're attracting people to change things, and a lot of them are really sticking with it. I'm going to go into detail about that in a minute. So let me first talk about what 3.9 actually is currently. So 3.9 will still be a GNU Radio 3 release. That basically means, if you know how to use GNU Radio 3.7 or 3.8, you feel right at home with GNU Radio 3.9. Like, it's the same blocks, it's the same work function, nothing really changed, right? Your code still works. You might have to name a couple of files differently, and you might have to wrap your C++ differently for Python, but it's still the same thing. You don't have to touch your core algorithms and core functions at all. It's not really 3.8, obviously, otherwise it wouldn't be a new release. So we dropped Python 2 support, which makes a lot of sense in 2020. We removed a couple deprecated blocks, and what we really did, and what I'm really proud and happy about, is that we moved Vogue out of Tree to be a library that has to be built externally. Like previously, that was always an option to build Vogue out of Tree, but we've made it mandatory now. So Vogue is our, in case you don't know, is our library that contains hand-optimized SIMD instructions for different platforms, and a dispatcher that automatically selects the optimum implementation for your specific platform after benchmarking. And it's very much encouraged now that Linux distros and other packagers package that separately, and hopefully that will make it easier for other projects to adopt Vogue. There's a couple of projects that already use Vogue, but we really want to, proliferate that. And of course, with the progression of our dependencies, we got the chance to update a bit of our tooling. So first thing, and that's probably where most of the line changes come from, is we dropped Swig and adopted PyBind 11. If you don't know what Swig is, Swig is our way, used to be our way of wrapping C++ towards Python and a bit back. C++ is not an easy language to parse, and it did astonishingly well, unless it doesn't, in which case it breaks in ways that we can't really trace and ways that are hard to understand, not only for users, but also for core developers. And every time something in Swig broke, there was basically half a man day in development off that we never got back. So I'm very happy that we now replaced that with PyBind 11, which is a C++ 11 construct library, which allows us to directly interface with Python, has much better error messages, and is basically from a Python user's point of view, at least as comfortable to use as Swig code. We replaced a lot of Boost constructs with C++ constructs, and a lot of manual memory and memory management with smarter pointers. And that was basically a lot of work done by Thomas, who just came out of nowhere and fixed GNU Radio in ways that I would have thought would take a long time. So I'm very happy. Thank you, Thomas. What we also did is we replaced the logging to standard output and standard error that was sprinkled all over the code through calls to our own loggers, which means that you can now redirect your logs so that your server logs contain if your, say, satellite base station kind of lost connectivity or whatever you're logging within GNU Radio. And as said, we dropped Python 2 support, and that is the other place where a lot of the file line deletions come from. There's a lot of compatibility code that we don't need anymore. So that was a big relief for every developer, because don't have to target two pretty different platforms there. So aside from changes, what are the cool new things that we bring? So first of all, we upstreamed, or this might be a bit of an overstatement, we're very close to upstreaming GRIIO, and I must say ADI has been super patient with me on that one. And what GRIIO does is it allows you to interface with IIO devices, which means basically if you've got an IADI device like Pluto SDR or one of their RFCOM dev boards or something, you can now natively use that from GNU Radio with in-tree modules. Then we've got GR Network, which at this point mostly contains better UDP and TCP blocks than we used to have, and that was really a necessity. And Mike, also did that more or less out of the blue after last year, and I'm so happy that we finally got that. So This is really useful. And of course, we've merged last year's Google Summer of Code, which means that now our mod tool has better ways of inspecting C++ headers, and also that has been very instrumental in understanding what needs to be wrapped for the Bind 11 transition. But yeah, let's refer to Josh's talk on that. And we improved a lot of functionality. This is just a random pick of things that I just popped into mind when I thought, what are the smaller things that we changed that people might care about? And like UHD supports UHD4 now. GRC has fixed its color problems. GRC has seen a lot of other fixes and improvements, really. So I'm so happy that GRC development picked up speed again. And there's a single developer whose name I personally don't think I knew now. That's JAPM48, and he's got hundreds of lines of code in there. So I'm super happy that this happened over the last year. And also, just very recently, we reworked our WAV file sync and source. That was Dr. MPEG actually. And now we're using an external library to parse and write audio files, also compressed ones, so you can now arc verbose stuff. And that is a big progress. Usually I'm very conservative about adding dependencies to GNU Radio because, it's already hard enough to package that. But with something that is so clearly the job of an external library as writing a specific set of files, it was pretty much a no-brainer that we should do that. So that's that. So, and then there's one thing in GNU Radio 3.9, and also that's partly also in 3.8, but it really happened recently, is that we've got examples for a lot of stuff that didn't have examples before. So, and that doesn't sound so technically advanced at first, but when you realize that this is the number one thing that something who's new to GNU Radio or to a specific functionality might need to get started, then you understand, the gravity of that. Because honestly, what Barry Dugan, we just met him basically at GRCon20 in Huntsville. He's been working day and night basically on improving the usability of GNU Radio through illustration, through documentation, through examples. And I think that as a direct result of that, GNU Radio has been more useful to a lot of users. And so maybe his work has actually been of, larger importance to a lot of users than mine on GNU Radio has been. So I'm very happy that we've got them. Thank you, Barry. So as said, we've dropped Python 3. We've dropped Python 2. We'll not drop Python 3, I promise. At least not very soon. We're progressing away from C++ 11 to C++ 14 or 17. Which one we pick depends a bit on the compiler situation. So we're still evaluating that. And we're removing a whole language, namely Swig. And that allows us and requires us to bump a few dependencies, but those are details. Basically, Boost, you need a bit of a modern compiler, you need a bit of modern CMake. It's more or less it. So 3.9 will not be much harder to build or easier to build than 3.8. But is that actually what I should be talking about here? Because mainly, I will write a changelog when we release 3.9 that contains basically everything that I said, maybe in a slightly different wording, maybe with a lot of stuff that you'd have to pick out between the lines there. But basically, this is not something that I need to be on record for. What's the things that I took away from the 3.9 process so far? And I try to condense that into 3 categories. So the first one is what's changing in the way the project works and produces code. Then what's changing in the users and the contributor base. And that's very much intertwined with the previous point. And the last thing is, where are we actively taking code development and where does it lead to itself for the nearer future? So these are the 3 things that I want to address here. So the first thing is what's changing. First, we obviously got a higher rate of releases that actually mean something. So this is really important for me. Why? Because first of all, it solves the issue of, I have a feature, I don't know when it's going to be released. Do I really upstream that if the return of on investment of effort here might not still fall into my PhD employment project, whatever. And I think that's a big thing, actually. Also, the rule that we add features to master first and then backport them to main 3.8 if it makes sense, has really paid out. I was a bit anxious about, maybe developers would be negative about, I've got this installed on my client's PCs and I'm developing this new feature, but it doesn't automatically go into the same release cycle as, these deployments feed from. But it turns out that people who are developing features often, prefer to use recent software and then are happy about the backport that they often do themselves even. So this has really paid out. We've got a lot of velocity out of that. Also, the fact that we've got proper testing now has really paid off. So our testing now is not perfect, certainly not. Like we have no hardware in the loop tests yet. We might be working on that pretty soon. But the fact that Andre and others put so much work into this really means that a developer who's contributing code, which works on their machine but not on anyone else's, now get an early feedback. And that's hugely less frustrating than, having to write an email, can I upstream this? Then getting back, no, sorry, this breaks on my machine and everyone else's machine, can you rewrite this and that? And it's less bottlenecky. So this is a really good thing, and it has opened GNU Radio development to a lot of people, and it has given us a lot of visibility also that we're on the right platforms there. And as a result, we're easier to add code to, right? So if you got better testing and got a higher cadence of releases, you're having an easier time finding a place where you can put your code. So while this is really a big improvement, and everyone who had to upstream something hopefully agrees, I know that we really need to be better about that. So that's why I said ADI has been super patient with me on the GRIAO thing. We've been less than stellar on coordinating that, and less than stellar in communicating, and less than stellar in consistency. Therefore, big upstreaming of external code bases. And yeah, that's basically it. We need to be better there and more consistent. That's mainly an effort in, say, concentration and documentation of internal processes for public consumption. Basically, we don't want to have internal processes. We want to have everything out in the public. So that's very clearly a thing that we need to improve. So also what we just managed to do is we have a live image again. So that was a commonly requested thing where I always had to decline and say, oh, I don't have one right now. I don't know whether I find a weekend to build one. Basti just went ahead and did that. And he did that based on just PPA. And I go into what a PPA is and why that's important on the next slide, because the last point on this slide actually is that our packaging has made sure so that it's easier to install things on more machines. And what that entails is, as I said initially, like GNU Radio 3.8 is available on every major Linux distro right now. So that's simply what you get if you apt install GNU Radio on Ubuntu 20.04. You can get an relatively recent, totally useful, absolutely supported GNU Radio. That's different from what it used to be. We have multiple different ways of getting GNU Radio onto things like OS X now. So like as the years before, a shout out to Michael Dickens, who's maintaining the Mac ports, and Kate Temkin, who's maintaining a GNU Radio app there. We've got 3 ways of installing on Windows now, like just native binaries. We've got Anaconda wrapping done by Ryan just recently, so thank you. And we've got the Conan stuff, which should work on other machines, I think, too. I've not tried it. I'm sorry, Bren. But Bren, watch his talks on FOSDEM, so you know what that's all about. And what we finally had is a PPA. So a PPA is basically Ubuntu's way of calling binary package repositories that are not maintained by Canonical /Ubuntu themselves, but by third parties, in this case us. And we've got a PPA that contains like basically the most current GNU Radio release for your Ubuntu, which might not already ship a specific version. So this is kind of cool because it means we can also say, oh, this might still need a bug fix on that version, and that's not coming for your Ubuntu, so please install this from the PPA. And it's a 2 lines of code operation that basically gives you access to that. And what just happened basically in the last 2 weeks is that Josh also built a PPA that rebuilds all the software in Ubuntu that already depends on GNU Radio against his version of GNU Radio, so that you can now say install GQRX and it will depend on the latest and greatest GNU Radio. And what that gives you is all the basics that you need to quickly build a GNU Radio Live image without having to do interesting things with building software and packing it into disk images and stuff. So that really was what Basti used to give you the VM image that you're probably using right now in the workshops. So what has changed in terms of the users and contributor base? So as I said, we've got 50 new users who hadn't contributed any code prior to 3.8.0 in the master branch. And that's a lot of new contributors for basically 13 months. So that's higher than what we expected. And what's interesting is that a lot of these actually stay. So they're not like one-shots, I fix my problem, I add my specific block and I'm gone. These are people that actually contribute consistently, repeatedly to code. And we're extremely happy that this is happening. And I thought like, is this just pure luck? And it really might be. Or is this also a result of changed processes? And I think it's both. Basically, like, people are awesome. I can't do anything about that. But the fact that we've got a matured development process with CI, with modern languages, with less stuff to slow you down, it makes it easier to contribute without question. And also the fact that we really took the jump into the Cold War and went in and reformatted the whole code with one consistent Clang format file. That means that you can now use your editor and ask it to produce beautifully formatted code, and it will just work. And that's also something that makes it easier on both sides to say, okay, this code works. It looks well enough. You had no choice in this indent, so there's nothing that can be approved. Let's merge that. And that's like a good thing. And I think it's very rewarding for people to get their code upstreamed without people having to politely ask them to please make indent it properly, for example. So, but probably indented code is not everything that a software project consists of, and especially not an open source and free software project. So we've got a lot of very technical contributions who aren't, exactly code. And as said, Barry has been doing a tremendous job of illustrating basically everything that you can do in radio. And together with Mark, who's leading our documentation efforts, we've now got a wiki that contains really useful documentation for every major block out there. So this is the documentation for GNU Radio blocks used to be, okay, this is the API, how you construct it, which helps no one if you're building a flow graph in GRC, towards something that actually looks like the documentation for a signal processing block that you'd want. So that's super awesome. The other thing that happened is that a technical way of contributing to GNU Radio is using it in a place where people who will contribute see it as a useful tool. And I've just picked, two very random things that kind of fit the theme here. The first one is GR Satellites by Daniel. He's been doing that for a couple of years now. It's a very consistently maintained project that allows you to receive and decode a metric ton of satellites telemetry. So this has gotten a lot of publicity, and there's a lot of very interested people seeing GNU Radio used as a useful tool, not only as something to prototype there. And that is usually contributing to GNU Radio there too. And also the fact that we're now, very closely working together with Zeni on, giving people access to their actual telescope arrays. The real SETI at home, if you ask me. That is so awesome. Thanks, Ellie. Thanks, Derek, for making that possible. And thank you, the SETI, for putting us in this position, right? So where are we taking this? Basically, there's two things to consider here. First of all, of course, there's the large future, and I'm not going to talk about that. I'm sorry, but there's two other talks following this one where you can learn more about that. I'm going to talk about things that will happen soon, right? After release 3.9, what are we going to do with GNU Radio? So first of all, we're going to fix the things that we didn't fix in 3.9, the upstream things that we forgot or didn't manage to. And I'm sorry, GRSOP. I promised to have you in 3 last GRCon. We didn't manage. Hopefully it happens, soon enough. I've got GRDPD, which is this year's GSOC project, and it will make a great addition because it's universally useful for everyone who has a power amplifier, which basically means everyone with an SDR. So there's pre-distortion that you really want to do, which is state of the art, and we should have had that functionality for decades. We didn't. So here we are. We had a GSOC, and we finally have the code in 3. So that's super, super awesome. Then there's a lot of other things that I think people will want to have upstream, and seeing that this has gotten easier, we'll see things like writing to files more smoothly, writing to more file formats, having more networking options, more transports, more accelerators, whatever. Maybe having something like PyTorch integration, because I think like the whole communication and ML thing, that's not over yet. So how is there a standardized way that makes sense for GNU Radio to interface to common machine learning toolkits? Or not. So that's something that we need to figure out sooner or later. Of course, like the code base is nearly 2 decades old. So there's a lot of modernization to be done whenever we touch something. And I think there is a lot of consolidation on modern C++ that will make working with GNU Radio more fun and quicker. So that's probably a good investment of our time. Of course, our packaging is something that is very dear to my heart, and especially can I have these nightly packages for Ubuntu that we have? Can we have the same for other platforms? Can we also, wrap the whole ecosystems in easy to install binary packages where people really literally just can apt install, say, GR satellites in the future? Can we have smaller builds of individual components? Can we encourage other distributions to behave like Debian in that they package GRDTV, GRQT GUI, GR analog separately so that dependencies are more granular? These are all things that we need to work with. And then as you can see, there's a lot of, code work, but it's also a lot of talking to other people work. And that's kind of, that's a challenge I'm looking forward to, but it's not an easy one. And as one specific point, so that you're not, really wondering what technical stuff goes on in my head, there's a consistent feeling that PMT might not be the greatest serializer out there, considering we basically only have wrappers for 2 languages, which happen to be the same languages that GNU Radio exists for, and that it's not really working on other platforms reliably. So we need to replace that with something faster, more versatile, sooner or later. But what's after that? Like, what do we do while we develop 3.10? What is the bigger thing that we want to achieve, right? What is the thing that we want to keep is the question that we should be asking here, because obviously we could rewrite everything from scratch and hope that, we survive that break. So what's the winning concept here? And I think it's pretty easy, and Basti's going to go into detail there. I think the block and the flow graph happen to be exactly the right level of abstraction. There's nothing to change about these. Like, they're perfect. Every textbook on communications just uses the flow graph consisting of signal processing blocks, and it's the right thing. What we have, however, is far from perfect. We're fixed on the wrong types of buffers, right? We can't have cyclic flow graphs, even if these cycles are not problematic. In fact, they're just problematic on an algorithmic point of view, or used to be problematic even, and we still don't allow them. We have a scheduling algorithm that really is no algorithm. We just tell the operating system to schedule the next best block however you want. There's no information flow to who decides what to schedule from how the state of data processing is, right? Everything has hidden state in the radio, and we can't just take a block and put it onto a different machine because we don't know what of this block state we need to transfer, and there's scheduling state, and there's block state, and there's mixed things, and that's no fun. We have zero ability to have transparent multi like cluster processing, so that's another thing that we need to solve there. And all our API choices right now make it impossible for us to change that. So we need to break API at some point in a major way. We can't be application logic compatible with GNU Radio 3.4 forever. And that's what the next two talks are going to be about. So thank you for your attention, and I hope you have a great conference.
Hello, everybody. So Josh and I want to give a quick overview about something that was started last year at GRCon, when Ben Hilburn led the breakout session about the future of GNU Radio runtime environment. And here we present a summary of what happened since last year. It will be pretty brief and high level, but there's this year another breakout session on Friday where we can go more into detail, and that will also be interactive where we can really discuss things. I hope some of you are interested and will join us on Friday. Okay, so when I think about GNU Radio, I'd say there are four main technical assets. Of course, there's the blog library where we have the efficient implementations of state-of-the-art DSP algorithms. And then we have the runtime that drives these blocks. It's running them in parallel to exploit multi-core CPUs, and it's handling the whole data flow. So these are the two core components of GNU Radio. And based on top of that, we build applications, SDR applications. For example, we have digital TV entry. There are popular out-of-tree modules for wireless LAN, LoRa, or satellite communications, and many, many more. And then finally, there's the ecosystem of software around GNU Radio. For example, GRModTool, which helps us create these out-of-tree modules, or PyBombs, and the whole effort around packaging GNU Radio that helps us to get GNU Radio on many systems, platforms, and distributions. And so from my perspective, there's happening a lot of very awesome stuff in a lot of areas. But one thing that seems to stagnate is the runtime. So let's look into the runtime. And in my opinion, the runtime was and still is the reason why GNU Radio is so successful. It allows to easily set up, configure, and run software-defined radio applications, and it offers a very decent performance. But at the same time, there was not a lot of development or improvement, innovation in this area in the last years. And I think this is not only because everybody is so super happy with the current state, but also because the runtime grew organically. So we added features here and there, and yeah, it became really hard to work on it and debug because some slight change here might break somebody else's applications in non-obvious ways. And with this being a very multi-threaded application, sometimes there are bugs that are not easy to spot and hard to reproduce, and therefore also hard to fix. So in other words, it's an area of GNU Radio where it's not so easy to work with. So before touching it, we thought, okay, let's take a step back and think about how we want to go in the long run. So how we think it, where do we actually want to improve and what do we want to change? And in my opinion, there are three main areas. One of them being the CPU runtime, obviously, because this is what GNU Radio was and is famous for. So like running an SDR system on a CPU. But I think in the future, we want to have a runtime where the runtime in the scheduler is not so closely entangled, but where we have a clearly defined interface that allows us to plug in different schedulers. For example, we might have a scheduler that's optimized for latency, another one that's optimized for bandwidth, or one that's optimized for a specific application, for example. Okay, then a second area is heterogeneous architectures, which means the seamless integration of accelerators, so for example like FPGAs, GPUs or DSPs. And of course we know there is RF-NOC, and there are out-of-tree modules like GRCL enabled or others that use the GPU. But all of them, they are not really natively nicely integrated in GNU Radio, but they are kind of hacked into it, let's say. And with this, there's always a performance penalty because the GNU Radio runtime doesn't know about anything else than its fixed buffer implementation. So it, for example, cannot directly write into accelerator memory. So this is a current limitation. And the third area, which might not be the thing we immediately work on, but that we might have in the back of our minds, is something like distributed signal processing, where a GNU Radio flow graph is not only running on one CPU on one PC, but it might span different PCs that are connected somehow. So for example, if one gets overloaded, a block might be transitioned statefully to a different node, and all the data flows are automatically rerouted, for example. And I think if we have these three improvements, it pays into what GNU Radio is already well known for, like straightforward implementation of SDR system. But maybe in the future, these SDR systems might be distributed and make more efficient use of the platform and its accelerators. Okay, so these are the 3 points that I think would be worth working on. But yeah, contributing to this part of the code is not easy, and this is a massive endeavor and major effort. But fortunately, there are also DARPA projects that are currently running, and these projects were initiated by Tom Rondeau. He was GNU Radio project leader for quite some time and is now program manager at DARPA. And two projects are particularly interesting. One of them is DSSoC, Domain Specific System on Chip, where they built a chip silicon that is optimized for a particular application or application domain. And the cool thing of these projects is that they don't only care about the chip, but they want to also develop the whole technology stack on tools that you need to program them. So from compilers, libraries, schedulers, whatever. So there are people thinking about, okay, how can components of the chip interact with each other? How can data flow? And maybe they think of schedulers that like how a particular part of the application, should it run on a CPU, a GPU, or FPGA, or whatever. So just with this example, you see that there are people who already think about very similar problems than we have. And for that reason, we started to talk to them and had some workshops where we were basically presenting the state of the art of GNU Radio and some of our ideas where how we could improve in the future. And we are currently trying to figure out if we can integrate some of their solutions or tools into GNU Radio. And there's also a blog post on the GNU Radio website that talks about these workshops, and it gives a bit more background on this topic. And then there's SDR 4.0, which is mainly driven by Blacklinks, and this is really tied to GNU Radio in the sense that they are integrating accelerators. So they are working on one of these particular areas that I was mentioning. They are currently focusing on the Xilinx and PSOC, but we're trying to come up with an approach that is more general, so that we can later also integrate GPUs, for example. And there was also recently a keynote by Tom Rondeau at New SDR. There's a link on the slide. And he's talking there about these two projects, but even more. And the interesting part here is that you see how these projects are part of a bigger puzzle that are Tom's vision for the future of software-defined radio and stream processing in general. So this might be interesting to get have a look at as a background. Okay, so now I talk a bit about our ideas for the CPU runtime, and then Josh takes over and talks about heterogeneous architectures and our current prototype implementation. Okay, so if you run a GNU Radio flow graph now, what happens is that GNU Radio spawns one thread for each of the blocks, and then from there on it's not really involved in any scheduling decisions, because then the operating system scheduler takes over, and then that's the thing that's deciding which thread is run on which CPU, how much CPU then does it get, and all these things. And this is pretty easy to implement, and actually also provides pretty decent performance, as we've seen in the past. The reason is that operating system schedulers are actually really, really good. But this approach also has some limitations that cannot easily be overcome. One of them is that you usually have a lot of threads. So on the right-hand side, you have an FM ODS transmitter, and even though this is a very simple technology, it already results in quite a lot of blocks, and with this, quite a lot of threads. And just using threads for everything also means that there are a lot of shared data structures. For example, all these buffers or queues that we use to get data from one block to the other, they require some synchronization primitives. For example, you have to hold a mutex, have to access a mutex to put something into the buffer. And this introduces some overhead that is not really optimal or might not be optimal. And finally, and this might be the most important one, is that the operating system scheduler doesn't know about GNU Radio or flow graphs or the structure of our flow graphs. So, for example, if you ran a block and it produced some data into the buffer, then intuitively it would now make sense to call the downstream block that reads this data and processes it, because then it could benefit from CPU caches, and this might actually be quite a big deal. But for now, we just have no control over it. So we don't have no control about the order in which threads are scheduled by the operating system. And one of the ideas we had to solve this is to introduce worker threads. And these worker threads, the idea is to decouple blocks from threads. And each of these threads might then be responsible to serve multiple blocks, for example. And this has two potential benefits. First of all, every data structure that's used inside one thread doesn't need any synchronization. And also, you have complete control about the sequence or the order in which data is processed inside the thread. So you could call a block and then a downstream block and actually benefit from CPU caches. And then a second point that idea that we had is to use like an inbox for everything that for all communication between threads. And this is sometimes called the actor model, and it's quite popular, and the reason is it's a good mental model to get multi-threaded applications right. It's much easier to think about a single inbox as opposed to many blocks that hold different logs for buffers all over the flow graph. So the idea is that, for example, there might be a message in the inbox that is a PMT that's supposed to be processed by one of the block's inputs handlers, or there is a message that tells you, oh, in this input buffer there's now 10 more samples available, or stuff like this. Okay, and if you adopt this inbox and this worker threads, there are already now scheduling decisions that you now have to make that were not there before. For example, one thing is that if you start a flow graph, you now have to decide how many worker threads do I want to spawn. Maybe just spawn threads corresponding to the number of CPU. And then you have to decide, okay, then I have a bunch of blocks in the flow graph, and then you have to map these blocks to worker threads. And here, for example, optimization might be that the CPU used by all these worker threads should be about similar, and at the same time you want to minimize communication between threads, because that, again, incurs some overhead. So that might be what I call the outer scheduler, which does this partitioning of the flow graph. And then you have another scheduling decisions that you need inside the worker thread, and this is you have to decide which block, the order in which the blocks are run, and how much data they are processed in, are supposed to process in one call to the work function. For example, here you could decide, oh, I give these blocks a lot of data, so maybe this optimizes throughput. Or you decide, oh, I don't give them just a small number of samples, so that might optimize for latency, for example. So these are then the scheduling decisions that you would have to make in this model. Okay, and finally, a very brief idea of how then the runtime would look like a pseudocode. So if you start a flow graph, you use the outer scheduler, as I call it, that partitions the flow graph and maps the blocks to worker threads. And then each worker thread is reading all updates from the inbox. and then it's calling the work functions of the blocks, for example. And at some point, every block, there might be nothing more to do. And then you could either check if there's something again in the inbox, or just do a blocking wait on the inbox, so on this one data structure, because you know everything that is interesting for your worker thread, you will somehow receive a notification through the inbox. So this is just a easy implementation of the runtime. Of course, that's much more to it, and we have ideas for I/O, blocking I/O. You know, this was a problem in the past. But yeah, maybe we can discuss this on Friday. Okay, so that was it from me, and now I'm handing over to Josh.
Hello, everyone. Thanks, Bastian. Thanks, Marcus. My name is Josh Moorman. I'm a research scientist here at Perspecta Labs in New Jersey, USA. And I want to talk a bit more about the heterogeneous aspects of the framework for GNU Radio 4.0 looking forward. So imagine, you have a platform that you want to run a GNU Radio flow graph on, and that platform has a variety of resources, FPGA, GPU, and we want that flow graph to be able to take advantage of all the resources at hand. So that's what we want this framework to be able to do in a native, straightforward, usable way. Now, if you take a look at a modern SoC board, such as the Xilinx MP SoC, it has a variety of resources. It has an FPGA, it has an ARM processor for general purpose processing, it has a real-time ARM, it has a GPU that may or may not be usable. So there's a lot of things at hand here, but getting GNU Radio to use these in its current state is, well, it's not that straightforward. So there's been a lot of one-off projects over the years to be able to get GNU Radio to run on an SoC, such as the MP SoC, but they've never really become part of the upstream, mainstream GNU Radio. And why is that? Well, one of the challenges with GNU Radio right now is, with coprocessors in GNU Radio, I should say, is that there's a double copy problem. GNU Radio has its own internal buffering scheme, and coprocessors are unable to get direct copy from blocks into their own device buffers. So there has been some great work in this area. I want to shout out to Seth Heitfield, who's been very involved in this effort of brainstorming about GNU Radio 4.0, and he did a presentation several years back about the custom buffers in GNU Radio. And the basic idea is that buffer pointers get passed into blocks for their input and output. Block does work; it's going to output into a circular buffer. GNU Radio has these doubly mapped circular buffers, and then the next block is going to read that buffer pointer in, do some work, so on and so forth. The idea with custom buffers is that buffer object, well, we want to get it directly into the CUDA buffers without having to copy into the GNU Radio circular buffers, without that extra mem copy. And so you take a look at that talk, and this is pushing forward this work is also one of the key aspects, as Tom Rondeau has mentioned in his new SDR talk, with the SDR 4.0 work that Blacklinks is doing. And so this hopefully is something that we can take advantage of early and get into GNU Radio 3.x upstream even before GNU Radio 4.0. But with GNU Radio 4.0, we want this to be one of the core the core concepts is the ability to avoid zero copy between work calls. And all kinds of different scenarios we want to address. CPU in and out of an FPGA, FPGA to FPGA. We might want to be able to copy from CPU and to FPGA and CPU at the same time, or FPGA directly to GPU. So it's all kinds of different processing elements talking to each other without having to go back and forth to the GNU Radio circular buffers. So one of the concepts that I think we're going to need in order to accomplish this in a very modular and straightforward way is this idea of domains. So basically, by domains, I mean I want some blocks to run on some hardware, other blocks to run on other hardware. And I think of domain as it's the encapsulation of all the resources needed for that portion of the flow graph. We want GNU Radio to represent the entire flow graph. But the processing can then be broken down and taken care of in different hardware resources. And in each hardware resource is going to need an associated scheduler, something that knows how to map to the memory of that, how to, maybe there's other security ramifications, latency constraints. So domains can be for a lot of different reasons, not just for different hardware. But a domain has an associated scheduler that then will call the appropriate block work function. So right now, everything in GNU Radio runs in the CPU streaming domain. Apart from maybe RF-NOC introduces this concept of domains. There's blocks that run on the FPGA. But we want to generalize that and make that part of GNU Radio. Kind of a necessary component of the flow graph is to say, what domain are you running on? So GR new sketch. This is where we want to work out a lot of the ideas towards GNU Radio 4.0. So this was an effort that was started at the Hackfest that Andre put together before FOSDEM last year. And we decided at this Hackfest that we're going to take a clean slate approach. We're going to, rather than being locked into the way GNU Radio is, we want to open ourselves up to new ideas that you might not be able to prototype very easily within the current GNU Radio framework. So this rewrite approach means that we're going to build things up based on the ideas that we come together and discuss, and have a sandbox, a real sandbox to work these ideas out that could eventually become something that looks like GNU Radio 4.0, or it could just be a sandbox to figure things out. Just don't know at this point. But take a look at this repo. I'll talk a bit more in the next couple of slides. So one of the key things that we are holding on to is the GNU Radio block library. As Bastian mentioned earlier, the block library is one of the awesome parts of GNU Radio. There's so many things you can just drop into a flow graph and use out of the box, on a CPU-based flow graph. We want to keep that basic construct of block as the atomic processing unit. And saying that we want to keep the same construct doesn't mean we're not going to change the API. We want to simplify the API, simplify the process of creating blocks, but the block still is a block. And what is a block? A block has a work function where you do your signal processing or whatever stream I/O. It has asynchronous message handlers, so you can set parameters or say reset your filter tabs. And it has some state. So like for a filter block, every call to the work function is going to update the filter tabs. So, the block library, we want to make the process of reusing all of the blocks people have developed over the years. We want to make that as easy as possible to get into the new framework. We don't want to come up with a whole new block paradigm. So then how do we get to GR 4.0? I mean, that's a big thing to think about. What we're really thinking about right now is how do we get to a minimum viable framework. We want to get to something to where folks can do scheduler research, where folks can develop a domain-specific scheduler for their specific hardware or their specific use case. There's a lot of pieces to GNU Radio that are involved in getting there, and even more that I haven't listed here. But I think it all starts with the core framework sandbox, this GR new sketch, just a place to work out ideas. And then that way, we're not locked into the GNU Radio way of doing things specifically, the current GNU Radio implementation, but we can do things from scratch, build up a library of all the other aspects of GNU Radio, and get to this minimum viable framework, a long while before we even think about what GNU Radio 4.0 is. In the process, we're going to learn a lot of things in doing this, come up with a lot of new tools, new widgets, things to fix in other blocks, And those we can percolate back up into GNU Radio 3.x. One of those could be the idea of custom buffers. We might come up with a good scheme for doing it, and that's something that we want to be able to get back into the current GNU Radio upstream. So just to summarize where we want to get to with this minimum viable framework, we want to get to a basic pluggable architecture, and a lot of these components can be pluggable. Not just schedulers. Blocks are already pluggable, but we want something where we want to get this API to where it works for all kinds of different scheduler designs. Get the scheduler API working for different scheduler designs. And I think it needs to be minimal. Doesn't have to have all the Python bindings, and doesn't have to have all the complete unit testing framework. But benchmarking is going to be a key here. So from the start, as we develop these constructs, we want to be able to test them. We want to be able to benchmark them and see how things get better when we can eliminate the double copies and we can run things on different coprocessors. But again, we don't want to break the block library. We want to keep the blocks in a way that they can be mostly reused from GNU Radio 3.x into GNU Radio 4.x. So here's the call to action. This is a huge undertaking. Starting from scratch and rebuilding GNU Radio in a reimagined, re-envisioned way. We've just started this. We've just started the last few months sketching out things in GRNU Sketch. We have a mailing list. We have a chat. So if you have ideas for how you'd like to get involved, or if you just generally like to get involved, reach out to me, reach out to Bastian, others in the team, and lots of things. It's a big project, and as we get folks that want to get involved, we can break down the problem and work on different aspects of it. So please reach out for longer form discussions. Reach out to this mailing list, and we can have an ongoing discussion about what the constructs, the ideas, the implementations for GNU Radio 4.0 and this modular scheduler concept are going to be. So thanks everyone, and enjoy your day.